My name is MegaZone. It actually is. I can even show you my ID afterwards. People call me MZ. Dale was originally going to be presenting this presentation. I guess he couldn't make it, so I stepped up to present his deck for him. So it might be slightly awkward because I'm only familiarized myself with it, but I didn't write it. This is cryptography and encryption basics. It is basics of cryptography. There's actually, if you already know crypto, there's like a black hat crypto attack session going on, I think, next door, which sounds actually interesting. I wish I could go to it. All right, so we're going to go over a brief history of encryption, and then kind of what is SSL and TLS, because I'm sure you hear that all the time now. And then looking at some of the TLS weaknesses and where we're heading in the future. So as a brief history of encryption. So prior to the internet, back in 700 BC, the Spartan military used sidetails to pass messages during wartime. And basically, for those who aren't familiar, you could wrap a strip of something around a dowel of a certain size or a staff or whatever your circular thing was and write your message on it. And then you'd also fill in all the other spaces with random junk. And then when you unwound it, it would just be a strip with a bunch of random characters on it. And if you wrapped it around something of exactly the same diameter, you'd get the message back. And that was very kind of weak encryption, I think. So then the Jefferson disk was developed by Thomas Jefferson as another early form of crypto, obviously analog cryptography. And then we had the Enigma machine, which is probably one of the most famous pre-internet crypto devices. Used multiple disks, internal wiring changes, different keyings, pretty complex machine, even by today's standards for a non-digital system. And it was kind of considered unbreakable until, of course, it was broken. The geniuses over at Bletchley. So MIT, back in 1961, the time-sharing system there had a username and password combination and also had an early software breach because of a bug in the software. So basically from day one, we've had problems with our security. So then we had the internet. So SSL was originally created by Netscape. I don't want to turn away from my mic. Back in 1994 to secure things on the early internet. For those of you who've been online that long, like myself, in the early days, people did e-commerce kind of in the clear. You'd send someone an email with your credit card number in it, because what the heck. But to really get things going and for the general public to get on board, we needed to have some way of securing things. And Netscape, being one of the pioneers in browsing and the web, developed SSL because basically they recognized that if they didn't have a way to secure things, commerce was not going to go anywhere online. SSL v3 was also created by Netscape in '95 because SSL v1 actually never got released because it was deeply flawed. So SSL v2 was developed. That was the first system deployed, but that also had a number of flaws. And once it went out to the public, because it was developed within Netscape, lots of people started poking holes in it and saying, hey, here's some problems with it. So the v3 was developed, released pretty quickly in '95. And that became kind of the basis for the growth and the explosion of the internet, because that was right around the time you started seeing URLs appearing on everyday products, and people who weren't network geeks were starting to say, what's this internet thing? Or what is that thing printed on that sign? So '99, TLS 1.0 came about, and basically because Netscape had shepherded SSL, but as SSL became vitally important to the internet, it was recognized that having it governed by a standards body would be a good idea, instead of a single entity, a single organization. So Netscape basically turned it over to the IETF, and that was standardized as TLS 1.0 in 1999. And TLS 1.0 was not too much of a change from SSL v3. It was kind of a codification of SSL v3 and like some of the errata that had been published and things. It was basically going, here's our baseline, we're going to start from here. And work began pretty much immediately on improving TLS. And we got 1.1 finally in 2006. 1.2 came out in 2008. That introduced a lot of new features to TLS, AES-GCM, which is pretty widely used now, and got rid of some of the problems we had in 1.1. Every generation keeps deprecating things that we find problems with. So the first real public exploits showed up kind of in 2008, right around the time 1.2 came out. So we started having all these exploits showing up. So in 2008, we had insecure renegotiation problems. We had TLS extension for secure renegotiation was introduced to kind of counter those problems. That came out pretty quickly. We had exploits like Beast and Crime showing up for TLS 1.0. That's one of the reasons why there was a big push to move to 1.1, 1.2. We had Lucky 13. There were RC4 attacks, so RC4 became deprecated or not recommended anymore. Time, which is an improved version of Crime, came out in 2013. We had Heartbleed, of course, which was one of the big ones from 2014. I was actually the engineer who handled our response to that at 5. And that was one of the big ones that started getting press. You started seeing like popular press and non-trade press talking about TLS vulnerabilities and things, and that was a lot of people who had no idea what was going on started seeing talk about the internet's falling apart. We had Poodle attacks on SSLv3, Dire Poodle or TLS Poodle on TLS, which came out right after that. The Freak attack, the Logjam attack, and basically it's been a nonstop parade for the past few years. So where are we now? Starting in 2015, Let's Encrypt launched, making it very easy for people to use TLS and SSL. It used to be kind of a pain and expensive in some cases to get TLS certificates, server certificates to put TLS on your systems. Let's Encrypt, the whole idea was basically we're gonna make this cheap and easy to maintain security. HTTP 2 came out in 2015, kind of rolling in some of what Google had developed in their own protocol called Speedy. It doesn't require encryption. That was actually in the earlier drafts. There was actually talk about HTTP 2 only being on encryption. That was kind of watered down, but pretty much all of the browsers, all of the implementations, de facto require encryption. So if you're using HTTP 2, you're gonna be encrypting things. Google stopped using RC4 and SSLv3. That's been widespread. Like if you're PCI compliant, you're not using SSLv3 anymore. You can't. Even TLS 1.0, I believe, at this point is now deprecated. Basically, they're pushing you to use newer standards. Let's Encrypt has hit 20 million as of last year, 20 million active certificates. And as of last Friday, TLS 1.3 was published. So that's been a multi-year effort. Finally got officially RFC status, 8446, as of last Friday. So we'll be seeing that now being pushed. And in fact, we released our 14.0 software sometime last week. I was at Black Hat and DEF CON, so I don't remember what day it was. But we actually have preliminary support for TLS 1.3 in there, but not the final draft support because of the timing of things. Like we didn't have the final draft because it wasn't final yet. And now you're reading these slides. So what is it? So SSL, or the basic functions of SSL or TLS. And you'll notice a lot of times, like SSL, even though technically what we're using today is TLS, it's still called SSL. Like everywhere it's in conversation, everyone talks about, oh yeah, we're using SSL for that, or we're using HTTPS, that's HTTP SSL. Odds are you're not, you're using TLS, but it's just like the generic way of referring to things. It's like Kleenex or something. So SSL provides confidentiality, integrity, and availability of the data over the connection. And so for availability, you're talking about authentication and non-repudiation because through the authentication mechanisms to the server or client and server in some cases. So some basic definitions. You've got SSL is secure sockets layer. And so that's Like I said, developed by Netscape in 1994 to protect your data on the wire. TLS is transport layer security. It was a standardized update, IETF controlled for SSL. Originally, 5246 was the RFC for that. And by sheer coincidence, and it really is, all of the TLS versions end in 46. If the TLS 10, 11, 12, 13, all the RFCs end in 46. For cryptography, so it's the science and study of transforming information in order to make it secure from intended recipients. So using, in our case, some kind of what you call a cipher, AES, RC4, or whatever cipher is being used to hide and provide confidentiality for the data. And then PKI, the public key infrastructure, that's used for public key cryptography or asymmetric key cryptography. And that allows two ends who've never spoken to each other before to create a secure connection to allow you to encrypt that data. So these are all like building blocks. So where is it in the stack? Now you've got your OSI model, your 7-layer stack. So you've got your hub switches, routers, proxies, and then SSL and TLS are basically at the session and presentation layer. So when you're going through and your browser's making a connection, it opens HTTP, the browser creates its HTTP headers and payload. And this is obviously a little bit simplified. I'm sure some of you are kind of going, yeah, there's more to it, but yes. That gets wrapped up if it's a secure connection in your SSL or TLS for its encryption. That's then handled over to the TCP stack for your network layer, your transport, goes into IP, and then it goes onto the wire, goes down, keeps going down the layer. So like everything else, it's basically a nesting doll of protocols. So it's built up of a number of building blocks. You have your symmetric encryption, like AES or ASGCM, or in older days, DES or 3DES, which, by the way, you should not be using anymore, or some other symmetric ciphers. Camellia is in there and some other possibilities. You have very symmetric encryption. RSA is pretty common. Your EC, elliptic curve, ECDH, DHE. Digital certificates used for authentication. In most situations, that's used to verify the server you're talking to. How do you know that you're actually talking to Amazon and not somebody who's man in the middle to your connection? There's message authentication codes on SSL that allow for data integrity. The digital signatures can be involved. The certificates obviously have a signature. Client certificates can be used if you're doing client certificate authentication. You can do certificate revocations are part of this connection. What happens if you issue a certificate or somebody issues a certificate and that certificate ends up being compromised somehow? Maybe that's been stored on a server that gets compromised. You want to be able to revoke that certificate because whoever steals it could then could impersonate that legitimate party. That's why you can revoke things. The different modes of operation, to talk about a little bit. PRNG, which is pseudo-random number generators. All digital cryptography relies on entropy. It relies on randomness. There is no such thing really as a pure random number. Most of the time in digital systems, you're calling it a pseudo-random number generator. It uses something it could use. If it's a hardware random number generator, it could use different hardware states at any given point in time. There are software algorithms that attempt to approximate randomness. Because the problem with cryptography or digital cryptography is if there's any predictability to it, if you had a non-random number, and this is a weakness that a lot of homegrown cryptography systems have suffered from, if you don't have randomness or something that approximates randomness, if you can start predicting things, you can start predicting what the keys are supposed to be, and then you can easily crack the system. So you need to have a really good random number generator involved. You have your certificate authorities that issue these digital certificates. There are a number of commercial ones out there, but like Let's Encrypt is pretty easy to use these days. And then at the top, it's all builds, it's all capped off with this is what forms TLS or SSL. All these little building blocks go into this. So what's actually happening under the hood? And by the way, I should say this up front, if I ever want to just interrupt me, just stick your hand up or shout something out, and I don't mind. So in a basic handshake, you have your client and your server. I'm sure many of you have seen this kind of diagram before. So you have your client hello. And it specifies when a client says hello, basically the client, this is the way it's supposed to work by the RFC anyway. The client comes in and says, hey, I'd like to talk TLS with you. The client should state the highest version it supports. Like most clients these days are going to come in and say, hey, I'd like to talk TLS to you, and I can support TLS 1.2. There might be a couple out there, I think Chrome and some others now, which will actually say, hey, I do 1.3 if you happen to do it. But most of the time, the client will come in and go, this is the highest version I support. These are the ciphers I can handle, and a couple of other options and things that are in there. But basically, the client comes in and goes, here's a menu of things that I can do when I want to talk TLS with you. No. No, in TLS 1.2 and earlier, no. I have a talk tomorrow afternoon on TLS 1.3 and what's changed there, and there are some changes there. But as far as encryption on the first packet, it's basically in the clear. If you use Wireshark, if you've ever debugged a TLS connection, you'll see the client hello, and it's, I want to support TLS, and I want to do these cipher suites and all. So at this point, you can't really encrypt it because the two ends, it's chicken and egg problem. The two ends haven't agreed on what to use to do encryption. There's all these options. So it's basically an in the clear. This is, I'd like to encrypt this connection. Here's all the ways I could possibly do that. Can you pick some of these? We work something out. So that's what the client sends in. The server responds, and the server will basically look at what the client sends in. In our case, the server would be the big IP. Looks at what the client sends in and kind of says, oh, okay, I can talk to that protocol with you. Maybe if the client says I do TLS 1.3, and the server says, I don't, but how about TLS 1.2? The server should respond with the kind of highest protocol version that's in common, or it'll step down to whatever its highest is if it can't do what the client asked for. This is how it's, again, RFC is supposed to work, because trust me, I've seen plenty of non-compliant implementations. And the server will pick from that list of ciphers and things that the client sent in. It'll say, sure, I'll talk TLS 1.2, and I see that you offer this cipher suite. You want to do ECDHC with AES GCM at 256 bits, and they'll basically pick from that menu and say, sure, I'll talk to you this way. And the two ends at that point can at least agree upon the foundations they're going to use to start building an encrypted connection. The server will also respond in that response. It will send its server certificate back, and that's use the server's public keys in there. The identifying things. This allows the browser to verify that the server is who it says it is. I'm sure many of you, if not all of you, have seen pop-ups once in a while like, hey, the browser doesn't like this. The server is saying it's so and so. You went to this URL, but the certificate says it's this other URL. Or the certificate's expired, or the certificate's somehow is a private certificate. It's not, I can't recognize who signed this, because it's basically what the browser tries to do is verify it. Every browser ships with a list of certificate authorities, root certificates that it recognizes as being able to sign other certificates. So if it gets a certificate that's signed by something it doesn't recognize, it should pop up a message saying, so-and-so claims to be X, it shows me a certificate that says to be X, but it's been verified by Joe Smith. I have no idea who Joe Smith is, so I don't trust it because I don't trust Joe Smith. Do you really want to trust this? You're the human, you tell me what to do. And so basically that's what the certificate does. It allows the browser to verify that it's talking to the right server and you're not being impersonated, you're not being hijacked. When the server sends everything it needs to send. It'll also send a message in there that says server hello done, which is basically tells the client, all right, here's everything I'm sending you. I'm done, whatever you need to do now. So then the client responds to the server with the client key exchange. That contains what's called the pre-master secret. This is where it starts negotiating the actual encrypted connection. As it starts, you have to have secrets to encrypt things. Each end has to know the keys that are being used. And it depends kind of on some of the things that are chosen in that first part of the handshake, that first client hello, server hello, what cipher are we using? Will help determine what is going to be in that exchange, the client key exchange. And it's encrypted. This is where things start to get encrypted. The client sends this to the server, and it will encrypt that key using the public key the server sent to it. And for those who aren't familiar with public key cryptography or asymmetric key cryptography, a small digression, there are two keys. There's a private key and a public key. And the names kind of tell you how they're supposed to be treated. The private key is the key that you keep secret. You should never let anyone see your private key. And the server has a private key that goes with its certificate. The public key is the key that you can give out willy-nilly, and you can post it anywhere you want. If you encrypt something with a public key, only the corresponding private key is supposed to be able to decrypt it in any trustworthy crypto system. So by the client encrypting this response using the server's public key that it got in the last message, only that server can then decrypt that. So at this point, you're starting to put some privacy in here. This change cipher spec message basically tells the server, hey, everything in here is from now on, we're going to start encrypting everything, send everything to me encrypted. We're going to use the ciphers that we've agreed upon. And from now on, this connection is going to be encrypted. So at this point, if you're doing a Wireshark debug, things get annoying because you're going to just see some basic packet headers, and everything below that is going to be an encrypted blob. And the server and the client says finished. So this is basically the handshake has finished. We've gone through, we've agreed on everything. Now we have an encrypted connection ready to go. We can start sending our data. It contains a message authentication code to provide data integrity for the messages that have just been sent. And the server should verify the message. It will basically look at the previous messages that it's gotten from the client. It will take that hash in the MAC, calculate itself, compare them, make sure that nothing's been tampered with, no one's played any tricks in the middle. And if the server's not happy with what it sees at that point, it should just terminate the connection. It's like, hey, we're supposed to be trusting each other, and your message doesn't validate. So either there's a real problem with this connection, you're doing something wrong, or there's a man in the middle. Either way, however this goes, we're not talking to each other. Depends on what you've going to go to. The specifics will depend on what you've negotiated in that first message, what cipher suite you're going to be using. Because Diffie-Hellman will have a different exchange than RSA, but it'll depend on what kind of key. Sometimes you'll generate unique key per session. Some clients will have a key they generate periodically, and they reuse that key for a little while. There's basically a cryptographic operation. If you ever use OpenSSL, there's command line things you can do to generate keys. So there are different ways you can do it. And a server responds with its own change cipher spec, basically saying, all right, yep, I agree with you. If I validated this, we validated it. Now I agree we are going to be talking cryptography from now on in encrypted session. And it sends its own finished message. And all this happens pretty quickly. And that's basically, all those arrows are actually 4 packets that go back and forth. Some of them could be sent in separate messages, but usually it's sent in one packet.
So where is the CRO checking happening?
The which check?
CRO?
The client would either check if the client is configured like a browser. A lot of browsers actually don't by default, but it would, when it gets a certificate from the server, it could check for revocation. By default, a lot of browsers don't have that turned on because it does add latency, because especially if you have it done to do a server check where it calls out to a revocation server to see, you're adding more round trips. Some browsers will update, they'll only push out, they'll have an embedded, they'll ship sometimes with also like an embedded revocation list, but it only gets updated when you update your browser, or some browsers might update it periodically. Like I think Chrome does that when it calls home because it always checks for updates. But it actually will vary from browser to browser. But the check, if it's done, is done kind of right after the server hello done, when the client gets the, after it gets the server certificate. And one thing that's not shown in here, this is a basic handshake. This is the kind of handshake you use almost all the time. This is most SSL connections, TLS connections. Use this handshake because this is what you're talking to any server you haven't talked to before. There's other things that could happen in here, such as if you're doing a client certificate authentication, where the server also asks the client to send it a certificate. And that might happen more in like a corporate environment where every employee is given a private digital certificate to authenticate with a smart card authentication or something like that. The server in its server hello will also do a client certificate request and ask the client, hey, send me a certificate. The client would then send it after client key exchange, and the server would then do a CRL check to make sure that that certificate hasn't been revoked. That employee is still actually an employee, whatever, that certificate's valid to let them in. And so at this point, we have a connection, and your application gated starts going. So once you have the HTTPS connection, usually is what it is, it's TLS connection in general. At this point, you're exchanging your application data. So this is your shopping, your VPN, whatever is riding on top of TLS. Yep. You want to get a picture of that? Rekeying will depend on configuration. Off the top of my head on Big IP, I know for some of the keys, we have a cron job that rekeys every hour. But it depends. It also depends on the actual, I think DHE is different from some of the EC keys. We have a couple different jobs on the box that rekey periodically. It used to be rekeyed a lot less often, but many versions ago. I don't think any version that's still supported is less than every hour. And there's also a flag in the configuration that you can set that says one-time use, where you can have it force a new key every connection. That has computational costs though, because you're generating a new key every connection. So most people don't turn that on.
So I understand the server is going to encrypt the packet using its private key action. The receiver is going to encrypt it using the public key, right?
Once you negotiate, I guess that's something I didn't touch on in there. The public key, in SSL TLS, there's two encryption systems used. There's public key cryptography and private key cryptography. The public key exchange, you use the pre-master secret, and there's basically a very brief public key exchange where you've generated and exchanged a private key that you then use for your bulk crypto. So like in this, we'll talk about Cipher suites next. So you have ECDHE there, and that's your public key exchange system. And so it's using Diffie-Hellman ephemeral, elliptic curve Diffie-Hellman ephemeral, to help exchange your keys. But as soon as one of the things you're doing in there is each end is calculating and generating an AES GCM private key. They're negotiating that and sharing that. As soon as you shared that, you're done with the public key system. Because public key cryptography is a lot more computationally costly. So, you're trying to get the best of both worlds. With public key cryptography, the nice thing is I can talk to someone I've never talked to before. I could do an encrypted connection with you because I can send you my public key, you can send me your public key, we can exchange, but the cost of the mathematical cost of computational cost of encrypting using that system every message is high. Something like AES is a much more efficient system. The problem with that is if I've never talked to you before, we have a chicken and egg problem. We have to have a shared key. So all you're doing is using the public key system to share that key and then you move on. Right. There's a session key. Yeah, once you've done that handshake with the initial, when you do that, where you do the client key, you send a pre-master secret, you basically use that to have your encrypted exchange, a very brief public key encrypted exchange, just to share a private key. And then once you do the change cipher spec, you're basically using a private key cryptography, whatever, like in this case it would be AES, or ASGCM, but whatever private key system you've negotiated, because then that's a lot faster. And at that point, you've now said hello to each other using public keys. You've already had that chance to share the private key, and you don't need public key anymore. And so that's where there's actually layers within the cipher suite. So this is this is like the full definition of a cipher suite. Yes.
And how do you eliminate man in the middle? Just a certificate? Is it what's
The client, so in most cases, in most applications of SSL and TLS, the concern is mostly that the server is going to be impersonated. Like you're going to Amazon, you're going to something, your secure mail server, whatever. So the client is validating that certificate, and that's really not the validation that's being done. That this certificate comes from the server, it matches the server, it's signed. And obviously, like if you have a certificate you got from a certificate authority and you allow that certificate to leak, you better get it revoked real quick. Because otherwise someone could impersonate you, because that's the only real check. If somebody gets a valid certificate that says they're someone they're not, they are that entity, like as far as browsers are concerned. So if I got a certificate, if I managed to somehow get a certificate that said my server is Amazon.com, no browser would be able to tell the difference. If it was a valid certificate. That's the trick, is that's why it should be hard to get a valid certificate.
the certificate has something encrypted in the browser?
Yeah, the certificates are signed by the certificate authority that issues them. And basically the browsers have a list of CAs, as they're known, certificate authorities, that they trust. And it's called, some of you might have heard the term chain of trust. So I trust this certificate, and that certificate signs this certificate intermediate, and that intermediate certificate signed this certificate, and that got presented to me. And so, okay, this certificate says trust this one, and this one says trust this one, and I do trust that one, so I trust the chain. And that's both the strength and weakness of PKI, is you have to trust that whole chain. And if you've ever configured a big IP of like a secure virtual server, one of the things you can do is you include your certificate. You can also include what's called the chain certificate, or the intermediate certificate chain, because you can actually include, just to make the life easier on the browser, you send your certificate, and in your server message, you also send all the certificates that link from your certificate back to the root certificate that signed it. And that makes the browser's life a lot easier, because it doesn't have to go out and kind of query things. It kind of goes, okay, I trust this, and here's the root I trust, and can I get from this root that I trust to this certificate with a non-broken chain? If it can't, it won't trust your certificate. If it can, it will. And so that's really the only real validation that's done on that both ends. And it's standard handshake. Again, I said there are variations. Like the server could also ask the client for a certificate, but that really only works like Amazon could ask you for a certificate, but how would they validate it? They have no idea who you are. Anybody can go out and get a digital certificate. That's usually only used in like a corporate environment where IT could give you a certificate in some way. And then you can prove that it's you by presenting that certificate back. All right, so Cipher suites. What am I doing on time? So we were talking about key exchange. So this is the key exchange agreement, and what's in this case, ECDHE is the public key system that stands for elliptic curve Diffie-Hellman ephemeral. Is used for doing key exchange, basically exchanging a private key. In this suite, the signature, what the algorithm used to sign things digitally, cryptographically, is called ECDSA. It's the elliptic curve digital signature algorithm. The bulk encryption, or the private key system used here, that's going to be used for most of the data, all of the application data that's exchanged, in this case is AES 256 GCM. So that's AES with a 256-bit key, using Galois counter mode as a particular operational mode for the cipher. SHA 256, which is SHA-2 algorithm with using 256-bit hash, because SHA-2 actually has multiple possible operational modes. It handles the message authentication. And then this bit at the end is, because there's elliptic curves involved, P384 is the name of the specific curve that's going to be used in this situation. There are other possibilities there. I could do a whole talk on that. Well, I'd have to do some research first, but it's a long topic. But the elliptic curve, there's different ways of doing public key systems. RSA is the one most people are familiar with. It's basically based on the factoring of large prime numbers. And, with RSA, you take two large primes, you multiply them, you get a multiplied factor that you can use as a public key, and only it's based on the difficulty of factoring that large number back into its base primes. Elliptic curve is based on a completely different mathematical principle. It's actually based on elliptic curves of a curve shape, and picking points along that curve and the relationship of what's the right word for it? Not dimensions, the coordinates on that curve. And so there's defined algorithms that define specific kinds of curves. Like P384 is basically an algorithm that defines a curve. And so it's, because both ends are using the same curve, this is where I probably explaining off the top of my head, you basically, using that as the curve as a basis of your exchange, you can exchange different values, and the other end can calculate back what you're talking about. I have to say that the math gets above my head. I'm not a mathematician. So like RSA I can get, I understand how that works. And there was actually really an interesting presentation last week at Black Hat or was DEF CON, I can't remember which one, that talked about not really breaking RSA, but using big data to break the keys, basically. And they're showing that there's possible now weaknesses with RSA with the computing power and data sets we have. That could be interesting. And basically their recommendation was use elliptic curve instead. So most of the time when you see a Cipher suite, the elliptic curve usually isn't listed out on the end because that's part of the handshake and negotiation. But when you specify a Cipher suite, like in a configuration, you'll see TLS might be left off on the front. Like on big IP, you probably see ECDHC_DSA, and the width might not even be there. It might just say AES256. But there's all the same thing. And under the covers, like all things with the computers, each one of these Cipher suites has a numeric value assigned to it. So when you actually look at the raw data in like a client hello in Wireshark or something, it's not like these words written out. Wireshark will helpfully interpret it for you and present them in English, but it's just like a byte value. There's a RFC defined table of what all the byte values mean. And like I said, the public key size is not actually part of the Cipher string. It's just on there for full representation. So why do the ciphers matter, or the Cipher suites? Well, if you can't negotiate a cipher that you both agree that you support, you can't talk with an encrypted connection. It's kind of like one-on-one. Like if you can't speak the same language, you're not going to talk to each other. Ciphers that are negotiated are taken into account by third-party scans. You ever get a PCI audit, or you run yourself through the Qualys SSL Lab scanner, or any of the scan tools out there, and you get results back saying you get an F grade because you support DES, or you get an F grade because you support this ancient cipher. You're doing SSL v3, whatever. You have to be careful what you configure, especially if you have regulatory issues. If you're handling credit cards, you have to be PCI compliant, or you get spanked. There are many different ciphers to choose from, and the order they're specified matters. Most of the time, I guess I can generalize this. There are two general ways ciphers are chosen. Like I said in the earlier slides, the client comes in and presents a list of ciphers it supports. It kind of sends the whole laundry list. This is everything I can possibly do. And if the server can't find one of those that it does, the connection fails. That's like bullet number one there. But how, if the server has, say it has multiple matches, like, okay, there are 5 of these cipher suites that I also support. How does it pick one? They're basically the 2 overarching rules there are either client preference or server preference. In client preference, the server will look at the list of client sends, find the first one in the client's list that it supports, and pick that. Server preference is the opposite. The server will look down its list of ciphers, find the first one in its list that is also in the client's list, and pick that one. Big IP by default is server preference. So however you configure the VIP, whatever order you put the ciphers in, if there's a cipher or certain ciphers you want to prefer over others, they should appear first in your list. Because it will always pick, well, generalizing, it will always pick the first one. There are ways to configure that differently.
So is that server-side preference on both sides?
No, because if we're the server, so and I know it's confusing, if we're the server, so if the client is talking to us, we get to pick the cipher. If we're talking to a server, like if we're the client proxying something else, it gets to pick the cipher.
So on the back end, the server is
In that case, if we're talking to a server, if we're proxying to the pool and we're doing SSL on the back end as well, whatever that pool member decides to use, we send it our list of what we want to support. And you can control that a bit by only configuring certain ciphers on the client, because when we're the client in that case, so in our client hello, we're only going to send the configured list.
But in your server SSL profile, you can configure
Yeah.
server client preference. You have that option.
Yeah, ultimately it's the server that decides, because in the server hello, it comes back and says, I pick this. Because the client, in every SSL, even if you say client preference, the server could basically ignore whatever you send it. The server always has last say.
Then why do you don't have that option?
I don't know. Because in the end, because the server could lie. Because you could send, I want to support all these ciphers, because the server could be like, oh, I only support this one. Because there's no way for us to know what the server actually supports, because the server never sends its list to the client. It only sends back, I pick this one. Ultimately, no matter what's configured, in the end, the server of any given connection has the choice, because it only sends back the one that was picked. And the client has no way of knowing how or why it picked that one. Some newer ciphers, which are often designed to be lighter weight for clients, especially because these days, these are our clients most of the time and not big desktop machines, can often be more computationally expensive on the server. So cost in a cipher algorithm is not always symmetrical. It could be easier for the client and harder on the server. And if you're operating at the big IP is the server, that's like elliptic curve is very much preferred these days. But elliptic curve costs more on a big IP than non-elliptic curve. Yeah.
But is there out there, like, out of the Cipher list, Cipher suite support on the M5, we actually recommend you only use these ones or anything like that?
That will change over time. I know there's actually a few Dev Central articles. I know David Holmes, who's a really, really good guy, has written a couple articles on that. Like how to get an A grade. I think there's an article out there.
Not just that, but just more like as stuff changes, like right now, I'm working on clients.
Right.
I just got all my clients upgraded from 10 to 11 to 6. And so I know between 10 and 11 to 6, there was a huge chunk.
Oh, big chunk, yeah.
That changed. But between 11 to 6 and now 13, 14, there's still even more slight changes, tweaks.
Yep.
I know I can take stuff that's a 13 and backrev it into my Cipher suite list.
Mm-hmm.
But is there like some sort of, hey, this is best practice to chunk out?
I don't think there's anything in general. Qualis, yeah, there's general, like not big IP specific, but there are general rules. Like elliptic curve is generally going to is generally going to be preferred for anyone over non-elliptic curve. if you use DES or 3DES these days, you're probably going to get dinged hard. Anything, you definitely don't want to be using SSL v3 or, like, God forbid, SSL v2. If you're using TLS 1.0, you're probably going to get dinged. At this point, my recommendation would probably be you want to use TLS 1.2 and not anything earlier. 1.1 if you had to. And some of it, of course, is going to be specific to people's environments. I've worked with customers where they have set-top boxes with embedded clients, and they can't be updated beyond SSL v3. What do you do? They have to support it. Then you have to take other measures. Can you restrict that? Is that a private network? Can you not expose those VIPs to a public IP address? What can you do above and beyond? Because you can't turn the protocol off. And so you have to look at meta stuff and how do we secure that. But in general, general rules are going to be larger bit sizes are more secure, but larger bit sizes also are more costly, so your TPS is going to go down. So if you do like a 2048 or 4096-bit RSA key, like you're going to take a lot fewer transactions than a 1024-bit RSA key. If you're going to do AES 256, it's going to hurt you more than AES 128. It's just the way it is. GCM, on the other hand, is actually lighter weight than non-GCM, so it's probably the best thing to go with. So the thing is, there's no easy answer because it's always a multidimensional trade-off, in how you do things. Okay. So there are weaknesses, and I didn't realize how small it was going to be when it was up here. So the CBC-based ciphers are cipher block chaining mode. And that's traditionally, most ciphers have been, other than RC4, which is known as a stream cipher, have been what's called CBC ciphers. They operate in cipher block chaining mode, and what that basically means is every time you compute a block of encryption data, that block is one of the vectors that goes into the algorithm for the next block to help encrypt that block, and then that block goes to the next block, so it forms a chain, which is cipher block chaining. There have been weaknesses found in CBC in general. Basically, there's always people poking at these things. Over the past few years, it's gotten clearer and clearer that CBC ciphers are pretty much on the way out. In fact, in TLS 1.3, they are gone. There are no more CBC ciphers allowed in TLS 1.3. Yes and no. TLS 14.0 has support for draft 26 of TLS 1.3, which is almost but not quite the final version because draft 28 became the final version. Yeah, I don't want to give version numbers, but I will say that it will be in the next version. The next, at least minor rev, like 14.1. I might go as far as saying it's already in the code base. Thank you. Yeah, it was just a timing thing, where 14.0 was in the release pipeline and the drafts came out. Like, we kept updating it until we kind of had to freeze the code, and it froze when 26 was then the current draft. But it's good enough at this point to play with a bit for testing. You're not going to see a lot of widespread client support just yet. So there's still time, but I think 14.10 will be out, and I probably shouldn't have said the version number, but whatever, with the full support, probably before you have any widespread client need for it, just because of client update cycles. So I got like 5 minutes. So there are all these attacks, Beast, Crime, Poodle, and Dial Poodle, which is attacks against padding on CBC. Lucky 13, which is a timing attack against CBC. Basically, CBC ciphers are becoming Swiss cheese. People are finding all kinds of principles by which they can be attacked. That's why in TLS 1.3, when they were working on it, they basically said, that's it, they're gone. The SSL v3, utterly and completely broken by Poodle. It's irredeemable. So that's why I said you should not be using that anymore unless, like I said, that customer with client-side set-top boxes. 3DES has been known for many, many years now to be really only 112 bits of strength. Actually, I've seen papers out there claiming to get it down to 110 bits of strength as opposed to 168. And now there are attacks, Suite 32, I think within the last year was that, time gets blurry, against any cipher with a 64-bit data block, which DES and 3DES both use, are now susceptible to the Suite 32 attack. RC4 is a stream cipher, considered widely to just be broken. Don't use it. SHA-1, starting again, I think over a year ago now, Google and Netscape, I believe, both started shaming sites that still use SHA-1. Like your browser would be like, oh, this site's using SHA-1, nah, you shouldn't do that. So like it basically was Google's gentle way. And also, for those of you who aren't aware, very recently, Google started shaming sites who aren't doing TLS. If you go to a site, instead of the old thing where it showed like this site's okay and this site's secure, now it's like this site is not secure if you go to a site that's not using encryption. So TLS 1.0, again, generally considered broken, Beast and some other attacks against TLS 1.0. TLS 1.1, there's nothing that actually specifically, it's sometimes broken. There are some attacks, depending on how it's configured and how it's used and what ciphers are used, that's vulnerable to. But TLS 1.1 is this weird stepchild thing because it was kind of a stepping stone to TLS 1.2. In fact, there are some clients, some systems out there that support TLS 1.0 and 1.2 and never supported 1.1. Or in fact, on Big IP, we supported 1.0 and then we supported 1.2 and then later on we supported 1.1. And that was because demand. And also one of our chipset vendors did the same thing. So we went with what they were doing. TLS 1.2, the protocol itself is not really broken. There are specific cases where implementations have been broken, Heartbleed, for example. So TLS 1.2 is still generally considered secure as long as the implementation is good and as long as you're using, like, TLS 1.2 will let you use single DES. It will let you use export ciphers, 40-bit ciphers, if you're crazy. So you can use a good tool in a bad way. But at this point, really, TLS 1.2 is what we'd widely recommend everyone be using unless there's some reason you have to use something earlier than 1.2. Yeah. Yeah. Yeah, you can do things. The only thing you have to be careful of is, and there are headers you can add. There's, you just have to be careful of forced downgrade attacks, where if you allow that VIP to support something earlier, that if a man in the middle, a client that could do 1.2 and do a really good cipher, somebody in the middle forces that negotiation down because you're still supporting RC4 and SSL v3 or something. And then that opens the connection to other types of attack. Diffie-Hellman, logjam, broke key exchanges. These days, it's generally recommended to use ephemeral keys, like Diffie-Hellman ephemeral, elliptic curve Diffie-Hellman ephemeral. So there are various attacks against components. So hopefully I have time to finish this. So the TLS 1.3, just to look at some of the changes, now you come through with very similar, you send your client hello, your supported cipher suites, you guess at a key agreement what the server will hopefully do, and you send a key share. It kind of tries to jump ahead. It tries to guess this is what the server's probably going to do. The server responds very similarly to before, with a server hello, computing the things it's going to use. So this is again where the client check certificate. It generates the keys it's going to be using for the connection to private keys. It sends the client finished message, and from there on, it's application data. You don't have to have a server response. It's a faster handshake. There are even faster versions of TLS 1.3. Sorry, I'm picking up speed a little bit. I'm kind of running out of time. So why do you want PFS, or perfect forward secrecy? Yeah, it's awesome. Oops, go back. So So PFS, which is also now TLS 1.3, this is one of the things that, depending on the cipher suite you chose in TLS 1.2, if you used ephemeral, like elliptic diffie-Hellman ephemeral, diffie-Hellman ephemeral, those were called PFS key exchange. That is now mandatory in TLS 1.3. There is no non-ephemeral key exchange. It means that every session has an ephemeral key generated for it, which makes it harder. And before, if you use something like an RSA where the rekeying happened every hour or things happen periodically, maybe some systems would rekey every day, every week, every month, or longer. If someone managed to recover that key somehow, they had captured all the traffic during that time period, they can then use that single key and decrypt everything. With PFS, there's a unique key used to encryption per session. So they'd have to, if they recover a key, it's only good for the session it was used on. And all the other traffic they covered, that key doesn't help with. So every session you want to decrypt, you have to recover a unique key for it.
So in years past, we used to private key and through like SSL dump.
Yep.
Or decrypt stuff.
Yep.
If you didn't want to hand out your private key, you could use SSL dump to go in and create that temporary key file that you could import from Wireshark. With perfect forward security coming out, is there going to be ways for us to put a debug mode into the LTMs that would generate one of those things that would decrypt things? Right now, the only way you can do it is to have perfect forward security, decrypt it, have another bit behind it, something like AS256, and then you put all your IDS stuff in your traces right there.
Yeah.
Just in bucket your decrypting, re-encrypting, decrypting. You've got a chain of 5, 6 bits.
Yep, I'm talking about that tomorrow in my TLS 1.3 talk. There is an I rule, basically, because there are 4 different keys in every TLS 1.3 connection. And you have to dump all 4. So there's an I rule that will do that. Now there are new hooks in the I rules that will dump all 4 of those keys. But it's also, again, per session. So yeah, the old trick of, even in TLS 1.2, you can say, oh, we're gonna change my ciphers to be only RSA so I can do debugging. Can't do that in TLS 1.3. RSA doesn't exist anymore. So with TLS 1.3, there's no more RC4, there's no more 3DES, there's no more RSA. Basically, all the things that have been shown to be weak in earlier versions of the protocol are verboten in 1.3. They're gone, they're not supported. TLS 1.3 is faster, can be faster. The handshakes are generally faster, there's less exchange going on, there's less overhead. There are some options that we don't yet support that are in the roadmap, like 0 round trip time, which is interesting. Again, I'm talking about this in detail tomorrow. ECC provides for smaller key sizes that have lower processing requirements, and ECC is definitely preferred now in our TLS 1.3. But you can also be using that in TLS 1.2 right now. It just depends on how you configure things like ECDHE and other options. So if TLS best practices, and I'll put these all up on the screen at once. So you only want to generate RSA or ECDSA keys. There are other options out there, but those are the 2 best. You really want to use 2048-bit or above for RSA and 256-bit for ECDSA or higher. You want the right type of certificate. Try to use certificates that are specific to your needs. Like if you can create a certificate that's good for a server, that's good, because some people will create a certificate that's good for every device in their domain, and that kind of creates a wide security umbrella for one certificate. For public key sites, again, use TLS 1.2 or 1.3. Try not to use anything earlier unless you absolutely have to, and really think about that. Definitely don't use SSL v3 earlier. Just keep it at least above TLS 1.0 unless you have some real good reason not to. Use PFS, so use ECDHE or DHE for your key exchanges. Obviously keep your private keys private. If you don't, you might as well not be using encryption. Certificate signing, when you get certificates these days, pretty much all the good CAs are going to require you to use SHA 256 or 384, 256 or higher, or even 512, but I don't think anyone requires that. So you shouldn't be using SHA-1. You shouldn't have been using SHA-1 for over a year now on any kind of certificate signing, but definitely not today. Use strong ciphers. Use AES-GCM, 128-256. Use good choices. Don't use DES or 3DES. And really encrypt all or nothing. And these days, again, Google has started shaming sites in Chrome. If you have any content that is not encrypted, your site will be shamed. So, and Chrome is the dominant browser, so don't be shamed. I think basically just at this point, there's no good excuse not to encrypt everything. And I am a member of the F5 security incident response team. There's actually a talk, I believe, in this room next about what that is. But we handle incident response for our customers have security incidents. And so I just wanted to put that up because my boss basically told me to.